സ്ട്രീമിംഗ്. റെക്കോർഡിംഗ് വേണോ?
റെക്കോർഡിംഗ് വേണം. പക്ഷെ ഇപ്പം തന്നെ റെക്കോർഡ് ചെയ്യേണ്ട ആ സമയത്തിൽ ചെയ്യാം അല്ലേ?
നമുക്ക് റെക്കോർഡ് ചെയ്യാം.
അപ്പോൾ ആ സമയത്തിൽ എന്തൊക്കെ മാറ്റം നിങ്ങളും ഉണ്ടാവും. പക്ഷേ
ഇത് ഈ ലെക്ചർ എന്താണ്
ലെക്ചർ അല്ലേ?
ലെക്ചറിലേക്ക് മാറ്റിയത്.
ലെക്ചറിലേക്ക് മാറ്റിയിട്ട് ഇല്ല ആദ്യം
ഇത് സ്റ്റോപ്പ് സ്ട്രീമിംഗ്
സ്റ്റോപ്പ് ചെയ്യണ്ട. സ്റ്റോപ്പ് സ്ട്രീമിംഗ് ചെയ്യണം. സ്റ്റോപ്പ് സ്ട്രീമിംഗ് അല്ലല്ലോ. തുടങ്ങുന്ന സമയത്തിൽ സ്റ്റാർട്ട് റെക്കോർഡിങ്, പിന്നെ ലെക്ചറിൽ മാറ്റാം. പിന്നെ ഇത് താരെ ഏട്ടാ അവിടെ ഗൂഗിൾ മീറ്റ്
അവിടെ ഇതിങ്ങനെ ഓണാക്കി വെച്ചാൽ മതി.
ഗൂഗിൾ മീറ്റ് അല്ലേ? ഗൂഗിൾ മീറ്റ് ഇങ്ങനെ ഉണ്ടാവും അല്ലേ? അത് ബോക്സൊക്കെ ഉണ്ടാവില്ലേ? ആൾക്കാർ വന്നെങ്കിൽ ഉണ്ടാവില്ലേ?
ഹലോ 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 ഹലോ
ഹലോ ഹലോ ഒക്കെ നോക്ക്.
റെഡിയാണോ?
കേൾക്കാനുണ്ടോ?
സ്പീക്കർ
എങ്കിലേ ഹലോ പറ. ഗൂഗിൾ മീറ്റിലേക്ക് കയറി
ഹലോ ഹലോ ഹലോ
ഉണ്ടോ?
വീഡിയോ ഓക്കെയാണ്, ഓഡിയോ ഓക്കെയാണ്. മൈക്ക് ഒന്ന് ടെസ്റ്റ് ചെയ്യാം. ഹലോ 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 റെഡിയാ? അപ്പോൾ ഇങ്ങനെ ഈ സ്റ്റാർട്ടിങ് സോൺ ഉണ്ട്, ലൈവ് ഉണ്ട്, ഗൂഗിൾ മീറ്റ് ഓണാണ്.
അത് സൂം അല്ലേ? അല്ല അത് യൂട്യൂബ് അല്ലേ? അപ്പോൾ അത് ഇപ്പം ഇതല്ലല്ലോ OBS
ഓബിയസിലാണുള്ളത്
അല്ലേ? ഇപ്പോഴെങ്കിൽ ഇത് OBS ആണോ? ഇത് ഗൂഗിൾ മീറ്റ് അല്ലേ?
അല്ല, ഇത് ഗൂഗിൾ മീറ്റ്. OBSലാണ് ഇപ്പോൾ സ്ട്രീമിംഗ് പോയിക്കൊണ്ടിരിക്കുന്നത്.
ഇല്ല അത്
മാറ്റിയിട്ടില്ല, ഇതിലുള്ളത്.
അതായിക്കോട്ടെ. അപ്പോൾ ഇത് സ്റ്റാർട്ട് റെക്കോർഡിങ് വെച്ചിട്ട് ഞാൻ താരെ ഈ ലെക്ചർ ആക്കിയിട്ട് താരെ വെക്കണ്ടേ? ആളുകൾ വെറുതെ ചെയ്യുമെങ്കിൽ അറിയില്ലല്ലോ. ഫേസ്ബുക്ക് ഈ ക്യാമറ എന്തോ പ്രശ്നം പോയോ?
చూసినట్టుంటే పనులు నాది వెంట్రాలపల్లి అదే దూరంలో కానీ 15-20 నిమిషాలు ఉన్నట్టే ఏమిటో దగ్గర
ഇത് ഇപ്പോൾ ഫസ്റ്റ് എന്നെങ്കിൽ
OBS-ൽ പോവാം.
OBS ഇതില്ല, OBS ഇല്ല, ഇതാണ്. അപ്പോൾ ഇവിടെ പോയിട്ട് ലെക്ചർ ഇപ്പോൾ സ്റ്റാർട്ട് റെക്കോർഡിങ് ചെയ്യാം അല്ലേ? ഇപ്പോൾ തന്നെ ചെയ്തോട്ടെ, പിന്നെ നിങ്ങൾ നോക്കാം. സ്റ്റാർട്ട് റെക്കോർഡിങ് സ്ട്രീമിങ് ആവാനുണ്ടല്ലോ, പ്രശ്നമില്ലല്ലോ. ഇപ്പോൾ പിന്നെ ഇതൊക്കെ രണ്ട് തുറക്കാം. ഇല്ല, ഇപ്പോൾ മൂപ്പർ വന്നെങ്കിലേ
അപ്പം ഇത്
റെഡിയല്ലേ?
അതിൽ പോയിക്കൊണ്ടിരിക്കുകയാണ്, ലൈവാണ്.
ഓക്കെ, അപ്പോൾ അതും അങ്ങനെ ചെയ്തോ. ഫേസ്ബുക്ക് ഞാൻ അത് ഓഫ് ചെയ്തിട്ടുണ്ട്. അല്ല, ഇല്ല, സൗണ്ട് മൈക്ക് അതൊക്കെ ഓഫ് ചെയ്തിട്ടുണ്ട്. റെഡിയല്ലേ? കുറച്ച് നേരം
യൂട്യൂബിൽ വന്നു, അതേപോലെ തന്നെ ഫേസ്ബുക്കിൽ വന്നു.
ഉണ്ടോ? ജസ്റ്റ് കുറച്ച് നേരം ഇരിക്കും. തുടങ്ങിയ ശേഷം
ആ പ്രിന്റ് വരാത്തോണ്ടേ അവിടെ ആൾക്കാർ ഭയങ്കര ക്യൂ ആ.
ശരി,
അവിടെ പോയി ശരിയാവില്ല.
ഇല്ല, ജസ്റ്റ് തുടങ്ങിയ ഒരു 4:30
ലൈവാണ്. ഇനിയിപ്പോ സാറ് വേറെ ഒന്നും ചെയ്യാനില്ലല്ലോ.
ഇല്ല, പിന്നെ സൗണ്ട് വന്നില്ലെങ്കിൽ ഇതൊക്കെ പ്രശ്നം.
സൗണ്ടിൻ്റെതൊക്കെ ഞാൻ സെറ്റാക്കി വെച്ചതാണ്.
റെഡിയല്ലേ?
ആ, ഇതാ സൗണ്ടിൻ്റെ ഇതിൽ തന്നെ ഇതാ ഇത്
റെഡിയല്ലേ?
ഓഫാണിത് ഇപ്പോൾ.
ചെയ്തോ?
ആണോ ഓഫ്?
ഇവിടെ ഓഫ്, ഇതാണ് ഓഫ്. ഇവിടെ ഓഫാണോ?
ആ, ശരിയാ.
ഓൺ ചെയ്യും.
റെഡിയാ?
ഓക്കെ. গুড মর্নিং, গুড ইভিনিং। শুনতে পাচ্ছি না, মাইক
হ্যাঁ এবার শোনা যাচ্ছে?
হ্যাঁ এবার শোনা যাচ্ছে, ঠিক আছে। তো কেমন আছেন?
ভালো, ভালো।
ভালো।
হ্যাঁ।
আপনি কি কালি মানে কেরালার দিকে এসছেন আগে কোনোদিন মানে?
না ওই একবার যখন কলম্বিয়া ইউনিভার্সিটিতে পড়তাম তখন ওই কোচিতে কনফারেন্স হয়েছিল,
আচ্ছা, আচ্ছা।
গ্র্যাভিটেশনাল গ্র্যাভিটি কনফারেন্স, বাট তারপর আর যাওয়া হয়নি।
যাওয়া হয়নি।
মেবি ওয়ান ডে আই কাম টু গিভ এ
হ্যাঁ।
রিয়েল টক।
হ্যাঁ রিয়েল টক, একদম মানে সামনাসামনি।
দ্যাট ইজ মাচ মোর।
হ্যাঁ আমরা এই প্রোগ্রামটা প্রায় 2 বছর ধরে করে যাচ্ছি, মানে হ্যাঁ অনেকদিন ধরে করছি। আর
দেখলাম প্রীতি আমাদের আইআইতে ছিল, এখনো টিআইএফ এ গেছে, প্রীতি মনোজ ওরা এসেছিল।
হ্যাঁ এরা এসেছিল সেই। তো অনেক লোক আসে মানে, আর এটা আমরা একটু ইনফর্মাল করি, মানে বলি যে কোশ্চেন করো কিংবা যাও যেমন যা মনে হয় সেগুলো করা যায়।
ফর বেঙ্গল অলসো উই শুড ডু সামথিং।
হ্যাঁ হ্যাঁ নিশ্চয়ই, উই শুড ডু। আমরা কি একবার স্লাইডটাকে চেক করে নেব? আপনি একবার প্রেজেন্ট করুন তাহলে, মানে অ্যানিমেশন ফ্যানিমেশন যদি থাকে কিছু ওইগুলো একটু দেখে নিই আমি আসছে কিনা।
আমি শেয়ার করছি।
হ্যাঁ
প্রেজেন্ট Google Chrome would like to record this computer screen. Asking for some permission.
চলো প্রবলেম হচ্ছে
শেয়ারিং এ আমি দেখছি, এবার শেয়ার করছি।
হ্যাঁ হ্যাঁ
দেখা যাচ্ছে না?
না এখনো কিছু আসেনি।
ও why is asking me your entire screen?
হ্যাঁ এন্টার স্ক্রিনটা করে শেয়ার করে দিন। ওই একটা নীল রকমের আসবে।
কিন্তু আমি যে ফাইলটা করতে চাচ্ছি দ্যাট শেয়ারিং
না ওইটা আপনি ফুল স্ক্রিন শেয়ার করে তারপর আপনার পিপিটিটাকে ডেস্কটপ থেকে খুলুন।
ও সরি, আই হ্যাভ টু ডু এন্টায়ার স্ক্রিন।
হ্যাঁ এন্টায়ার স্ক্রিন।
Share your interest. Chrome wants to share the contents of the screen. Wait, yes. Can't share your screen. Can you make it me presenter?
হ্যাঁ প্রেজেন্টার, সেই তো আপনি প্রেজেন্টার, হাতে কিছু করার দরকার নেই, আপনি শেয়ার করুন। এনিবডি ক্যান শেয়ার, এখানে কোনো অপশন মানে ও দেওয়া নেই আর কি, খালি ওই অ্যারো যেটা আছে ওইখানে।
ইট ইজ আস্কিং মি টু গো টু, আমি ম্যাকে করছি, আস্কিং মি ফর এ পারমিশন। allow the apps below to record content. Okay, will not be able to record. You can hear me?
Yes.
Excellent. But
I can hear you, but you have to see the sharing.
You see now?
Yes. Yeah. Now you can. Yeah, it is fine. Fine. Okay. You can make it full screen. Full screen. You make it.
Full screen.
Yes. Perfect. It is perfect.
Now, just let me see. Can you get the video and see the video? The next is video coming.
Okay.
I'll show you.
Yeah. Yes. Yeah. I can see. And here also.
Most of us.
Okay. Sound is also there.
Okay.
Yeah.
Then everything is fine.
Any other animation? No.
There is later, but it will be coming in the same format, so not a problem.
Okay. Fine.
Okay.
সো 5 মিনিট একটু ডিলে করব কেন কি সাধারণত 5 minutes people take to come
Yeah.
in, so we will allow them so that they don't miss.
Who will be the participants mainly? I have said.
Participants will be from throughout India. We are sharing it at various platforms.
Okay.
So many people like college students, school student, teachers, other professionals, everybody. So it
Okay,
is shared.
great.
Yeah.
And last at the end, question answer will
Question
happen.
answer normally in this AstroAdda, what we say, since it is Adda, we say that you can stop the author and speaker and ask question. But
Yeah.
if you can wait up till the end, that is good. So
Exactly.
at end we will give you a lot of time to ask question. But if you can't, if you are thinking that that question is very relevant at that point, you can't follow, then of course you can ask questions. You can interrupt.
Okay.
ঠিক আছে?
So there will be people from YouTube also directly. They can ask.
Yeah, they can also ask questions.
So somebody can read some question if needed.
Yes, if needed. Yes.
They can ask. Yeah. Okay, good.
Okay.
So now all set.
All set. So we will wait for some time, say 3-4 minutes, and then I will start the program and I will welcome everybody, introduce you, and then we will go for the talk.
Yeah.
Okay.
So now I will stop sharing or it will continue?
You can stop sharing now, like that. Yeah, that's fine.
Okay, good.
Yes. So I think we can start. So welcome all of you to today this AstroAdda program for this month of October. And you all, many of you have been with us throughout for many of the talks which we have been conducting, and very enthusiastically all participated in lot of interaction with the speaker. So that was a good sign. So today we have a very good speaker with us, Dr. Professor Subinoy Das, and he will be delivering a talk titled Mystery of Dark Matter and Dark Energy. It's a very interesting topic, and it's the modern topic in which a lot of work is going on. So I'll just introduce our speaker. Professor Subinoy Das is working at Indian Institute of Astrophysics for last 9 years as an active researcher in cosmology. His main research area involves detecting mysterious dark matter and dark energy. He has done his MSc from IIT Kanpur and then MPhil from Columbia University in New York and PhD from New York University. After that, he has spent 5 years in Canada and Germany as postdoc fellow. He joined Indian Institute of Astrophysics Bangalore as faculty in astrophysics, astroparticle physics. He has given many public talks and is very interested in outreach to people who are fascinated by universe and its beauty. So, Professor Subinoy Das, the dais is yours, and I think you can start presenting the topic.
Okay. Thank you so much. Thank you RSCP for inviting me and giving us opportunity to talk about one of the most fascinating topic of cosmology, which is not totally known, and that's why it is very interesting. And let me share the screen today. And you can hold, if you can hold on to your question, then I will finish the talk in 45 minutes or 40 minutes. You can write down the question, because throughout the talk many things might be answered. If it is not, you can definitely ask me at that. So let me share the screen. Yeah. So you can see the screen, I hope. Yeah.
Yeah. Yes, we can see.
Thank you. So the topic today is called Mystery of the Dark Matter and Dark Energy. And how do we know that they exist? And what will be the fate of our universe? And what is the role of dark matter and dark energy in our existence? And that will be the talk today. And you will see that for the future generation there are a lot more to do. I'll start with a joke. When I was a graduate student, that time people did not know about dark energy. And dark matter, it is more or less getting confirmed. So that time when I used to look into the, that time internet was also not available, and I used to look for the newspaper, the state of the universe, how the Stephen Hawking's book. Then that time we thought that we understand most of the universe, only few percent is unknown. And then I went to New York after Kanpur IIT. Then after, when I was finishing my PhD, then we realized that we only understand 4% of the universe and 96% is unknown. So as we more know, we are pushing the boundary to the unknown, and that's beautiful because there is so much to know, so much to do. So these are the fundamental questions that everybody asks. You don't need to be an astrophysicist. I'm from rural Bengal, when the load shedding power cut used to happen, then I used to go to the rooftop, and that time the pollution was not there. And even you can see the spread of the Milky Way galaxy. And this question will come to me, and I think for many of you, that what we are made up of, how we came from, and what is our destiny. And today in this talk today, I will show you that the dark matter and dark energy has huge role to play, at least the last two questions, what we are made up of and what is our destiny. But before I move to the final conclusion towards the end, let me give you the conclusion in the beginning, because generally people lose attention after 5 minutes in many talk. So I would like to give my conclusion even before 5 minutes is over. So if you look into our universe, suppose this is called cosmic cake, only the orange strip here is of 0.5% is all the billions of stars we see or we can see in future, so-called the visible universe. And other than that, 4% is hydrogen and helium gas, in especially intergalactic medium, between galaxies or galactic, they are called intergalactic medium. So this is basically more or less 4% of the periodic table, which we know that the periodic table is making only 4% of the universe. So 96% is remaining. Out of that, 27% is dark matter, and remaining is the dark energy. You can see the blue. And neutrino only 0.3%, and that is also mysterious. We don't know what is neutrino. Is a photon-like particle which has almost zero mass, moves in the speed of light. And the heavy element of periodic table towards the end of the periodic table, which is xenon or like which has higher atomic number, they are only 0.03%. Like lithium also, we sometimes call in cosmology, after hydrogen and helium, everything is heavy elements. Okay, so you can see that, so like almost 96% of the universe is unknown, and that is dark matter and energy. This is a NASA figure. So basic fact, before we go into that, basic facts about our universe. It is very big. How big it is? So from one side to the other side of the universe, then you are asking, does the universe have a boundary? Universe does not have a boundary, but visible universe has a boundary. Because of the Einstein's theory of relativity, there is a limitation that how far we can see. Beyond that, we cannot communicate, because beyond that, the velocity is faster than the speed of light from Hubble's law. So even if the stars beyond that is throwing light to us, but it will not be able to reach us. So we have a finite boundary of the universe where we can communicate. But it doesn't mean there is nothing beyond that. So the finite boundary of our universe is 30 billion light years. I have put in so that it's those who cannot fathom billion so easily. So these much zeros are there. You can see it. So many miles. Just to give you an idea that light, this is like at so many billion light years. That means so much light, so many years light take to travel from one end to the other end of the universe. Just to give you an idea that light, you all know, light travels 186,000 miles per second. And if you calculate from there how much light can travel in 1 year, it is 6 trillion miles. So many zeros you can see. I'm not reading. And with that speed, with the speed of huge speed of light, 8 minutes is the distance between sun and earth, you all know. So now you can imagine that 30 billion years light has to travel to cover our universe. Even to cover our own galaxy, Milky Way galaxy, it takes million. So million means 10 lakhs here. So if light travels from us to the other end of the galaxy, your so many next generation will be gone till light cannot even travel to our tiny Milky Way galaxy. It is not tiny, but compared to the universe, it is tiny. So big and huge is this universe. And that's why when you look into the universe as a whole, here the tiny dots are called galaxy cluster. Means there are many galaxies in cluster. One is Virgo cluster, you cannot read it, the green one in the middle. So this just looks like a dot, but Virgo cluster is huge, means not only one galaxy, many galaxies is there, but that looks so tiny even compared to the universe. So you can feel that how big is our visible universe. This boundary I have drawn on the basis of Einstein's theory of relativity. But beyond that, there is also many galaxies, who knows, there might be universe. And that towards the end I talk about it. It's called multiverse. So now, if you see here, you can see the structure. If you take a microscope, and that is our telescope here. For biology, we use microscope. It's almost looking like a cell, and here, if you take the microscope in, then you will see Milky Way. There are 10 billion stars in our Milky Way. Even one dot here is huge, and there are billions of stars there. So it has structure. It has beautiful structure. I will show the structure a little bit later. But there is a beautiful saying. Some book recently came out about the structure of reality. So the title page has this quote. I forgot the author's name. That it says, "What has structure, beneath it has more than structure." So I repeat, what has structure, underlying it has something which is more than structure, and that's why structure can arise. So here, the structure maker is empty space, and that is the beautiful discovery of Einstein, that space is not just a spectator, which Newton thought space is just a drama stage, and it does not interfere with the actor. Like in movie theater, when you go to see a drama, you see the stage does not interfere. Stage gives the platform. But in cosmology, in our universe, the empty space is also not only the stage, but it also the player, one of the player of the drama of universe or life. So what does it mean? So before we go there, let us look into the space. It's a beautiful video that all we have is space, but still space is not so visible. You cannot see space, but you need space for things to be. And how much space is there? This video will tell you how much space is there around the structure.
When most of us picture space, we think of outer space, a place that's far, far away. But space is actually everywhere. You could say it's the most abundant thing in the universe. Even the tiniest of things, like atoms, the basic ingredient in you and me and everything else we see in the world around us, even they are almost entirely empty space. In fact, if you removed all the space inside all the atoms making up the stone, glass, and steel of the Empire State Building, you'd be left with a little lump about the size of a grain of rice, but weighing hundreds of millions of pounds.
So you can see from the video that if you squeeze the whole Empire State Building of Manhattan, which was the highest building when I went, because 9/11, after 9/11, that was the highest building. It will be just in grain, and if you squeeze. And that's the idea of black hole. If you squeeze our whole Earth, it will be just like a matchbox. If you squeeze a big star, which is more than the 1.4 times the mass of the sun, when you squeeze, it will become like a few kilometers. Not even the Bangalore, but whole Bangalore I'm talking about. It may be just the campus. University campus, and that is a black hole. So when you squeeze, because huge gravity can make the space curved and the light cannot travel from it, so much attraction. So that's the idea of space, but till now I haven't told you the main discovery about the space. But before that, one beautiful thing we came to know, that this space, which is the platform, it is not static, it is expanding. And here is a beautiful picture. Einstein's looking at the telescope, and background is the Hubble. Hubble discovered the expanding universe, that everything is moving away from each other. That means space is actually expanding, like a balloon is expanding. So everything, every dot on the balloon has to move. That's the modern understanding of space. So Einstein, when he discovered theory of relativity, general theory of relativity, he believed that universe is static and eternal. But when he wrote down the equation of the space, he was not getting the solution of a static space, means he was getting the space is expanding. But that time then he said, no, but I don't see space is expanding. That time Hubble did not discover the expansion. And he also believed that space should not expand. Can you hear me? Just there is a.
Yeah, we can hear you, but
Okay.
nothing is seen in the screen.
Okay, I will come. Something happened. And we will take it. Sorry for that. Yeah. Sorry for the disturbance. You can hear now, right?
Yeah.
Yeah. So, this space, empty space, which Einstein was believing, is actually wrong picture, because Einstein added an extra term to stop the expansion from his solution of the equation. But later, Hubble came to know from his telescope that space is expanding, and Einstein had to take out that term off, and it is called Einstein's greatest blunder. Einstein used to call it cosmological constant, which he added. But even the blunder of a genius is very interesting, because we have to add that term again back few years before. But on the other side of the equation, it is called cosmological constant, but with the opposite sign, which Einstein put, because now we realized space not only expanding at present time, it's a Nobel Prize few years back, that space is accelerating, and so the velocity is even increasing. It is a positive acceleration, and that's very mysterious. It is as if your car is going and somebody has pressed the acceleration button of the car. And that is the dark energy, and that is very mysterious, and it has a lot of things to do with our existence. We'll come to that. So these are the basic idea about space. The space expands in all directions, it's dynamical. It is the property of space-time itself. You cannot stop that. So this is very beautiful. What seems static in naked eye, everything is moving. Atoms, the nucleus around the electron is moving. Even in the nucleus inside, those who are particle physics students, they know that inside the nucleus, the quarks are huge speed moving, and because of that only the nucleus is so heavy. Nucleus is made up of 3 quarks. If you add the mass of the 3 quarks, that is much less than the mass of the proton or neutron. It's the movement of the quark inside, the kinetic energy we call it in physics, that is giving the mass of the thing. So everything is very dynamical. Only one thing left was the space, because that's the stage. But even in nature, the space itself is dynamical. It can turn, it can twist, it can expand, and you cannot sense it with our 5 senses, because 5 senses cannot see space. It can see things in space, it cannot see space. But with observation, with instrument, with indirect observation, we know that will come later. The space is expanding and it is accelerating. And there are few questions to think about, which I cannot answer today. You can maybe WhatsApp me later. That what this space is expanding into. Is there something else? Is there a boundary of the universe? I said yes, from observational point of view. But beyond the observation, is there a boundary? Or if you keep moving, you will always find some galaxy stars. And how far can you communicate? That I have told you. That is our digital pulverized. So now let us move. I will play a video. It is also made by my advisor, PhD advisor Brian Green, whom you saw in the last video. It's from Newton to Einstein. Newton's gravity of apple fall, everybody knows, but Newton was not so right, as I told you. So let's see this video, and then it will be clear that according to Einstein, gravity is not a force, but just the mere dance of space and time. When the space bends, then the Earth and Sun feels an attraction between, and that's called gravity. But according to Newton, it was a force. Newton ignored the space and kept it as a spectator, and like a darshak, that who does not participate, witness. But Einstein said no, it's the space which makes the things move.
And long before Einstein, the quest for unification began with the most famous accident in the history of science. As the story goes, one day in 1665, a young man was sitting under a tree when all of a sudden he saw an apple fall from above. And with the fall of that apple, Isaac Newton revolutionized our picture of the universe. In an audacious proposal for his time, Newton proclaimed that the force pulling apples to the ground and the force keeping the moon in orbit around the Earth were actually one and the same. In one fell swoop.
So this is the beauty of Newton. He combined celestial with celestial. Means heaven and earth become one. He said it's the same law which governs the universe.
So racking his brain,
But after that, Einstein
he found the answer in a new kind of unification. Einstein came to think of the three dimensions of space and the single dimension of time as bound together in a single fabric of space-time. It was his hope that by understanding the geometry of this four-dimensional fabric of space-time, that he could simply talk about things moving along surfaces.
So here you can see that I just showed you that the earth is moving around the sun, not because there is an attraction, but more deeper level, because the sun shifts the space curved. And as you know, if a bed sheet is there and if you put a solid iron ball, the bed sheet will be curved. And if you put a marble, then the curved marble will move automatically. And if you give it a kick, then it will move like a velocity, like in the fair we see motorcycle moving in the well, like that. It's exactly the curvature which is making the universe move. So its curvature means what? The curvature of space. This is revolutionary because nobody can imagine that the space, empty space can dance like that. And that's theory that even you can write a mathematical equation that how much it will be curved, and that is called general theory of relativity. And with that, Einstein discovered the presence of black hole. And not only that, he said that when the curvature will be so high, then even light cannot come out of it, and that is called a black hole. And then he also predicted that this black hole, when they merged, or because of the dynamics of the black hole, there will be some waves called gravity waves. And that has been discovered and given only a few years. And India has also been doing active research in that. And government has a huge funding for the next generation gravity wave detector. So now, what happened in the beginning of the universe? I'm going in the very beginning, and the space was not there, or you can imagine, space was very, very tiny. And then space was stretched to a huge platform, and that stretching is called inflation. Not the financial inflation, but the inflation of space. Means fraction of a second, the space was stretched to almost infinity. And the origin of the space, those who know, it's called quantum. Quantum means is topsy-turvy. You cannot measure anything there. When you go there, everything is random there. So there was a fluctuation, and when this fluctuation was stretched, you can see the tiny fluctuation after being stretched with yellow, with green, and the blue part. Means some part will be high density, some part will be low density, some part will be high temperature, some part it will not be homogeneous exactly. And that was the prediction that the space-time came from almost nothing. It was created in the Big Bang, during the Big Bang. And after that, this hot Big Bang was given to us, and that was the view of the baby universe. And that has been detected by two satellites, WMAP and recently the European Space Agency Planck satellite. And first it was detected by 2 engineers, because it was predicted that if these inhomogeneities are there in that, and then there will be a fossil radiation, because the universe is expanding and the universe is cooling down, and that is called cosmic microwave background radiation, and it should be there, and that temperature or the wavelength will be temperature will be 2.75 Kelvin, and it will be in microwave range. But nobody cared about it, because this was a theory that time. Nobody thought about it. Long back, these 2 engineers in Princeton University, they were electrical engineers. They were looking for some signal in from. They were exporting antenna, electrical engineer, and they were probing something from the sky. I don't know what. And they got this noise of 2.75 Kelvin, or the microwave noise. Then they moved their antenna to somewhere. They again getting that noise, and then they moved the continent. Maybe they thought it is just a disturbance in the local sky. They moved the continent, they got the noise. Then everywhere, in every direction, they are getting this radiation of microwave. That means it cannot come from one particular source. It has to do with the origin of the universe, because it is coming from everywhere. Because origin has been expanded into everywhere. Because origin, there was no space or very tiny. And that was, then they looked into it, and people said that there was a prediction that if Big Bang really happened, and then fossil radiation will be there, and you will see this microwave radiation, which belongs to a temperature of black body spectrum of 2.7 Kelvin. And they got the Nobel Prize. So they were engineers, they were not, so this is like serendipity, like they were not looking for a discovery, but it happened. So this is the idea. Here the WMAP satellite. Then after their discovery, the NASA and the European Space Agency has spent billions of dollars to measure that fossil radiation in much higher accuracy, because it contains the information of the whole universe in a very mystical way. Not mystical, means for us it's mystical, but when you know the science, you will see that the cosmic microwave background, this pattern on this blue-green pattern, you can decompose that pattern and find out the information about dark matter, dark energy, in the beginning of the universe, how was the expansion rate, and many things. And it is fascinating that we are now here on the right side. 14 billion has passed by, but that radiation is still coming to us, because there is nowhere else to go. You will only rotate inside the universe, because I'm not going into it. Whatever is in the universe, it will not leave the universe. Okay, so that light are still coming, and we got they got the Nobel Prize. In a little bit more detail, here you can see the red arrow is the time, so 0 is the beginning of time. So you are looking back into that radiation, and if you see this history of our story of our universe, just like a baby is born and then become little 1-2 years old and then go to school. Like that, our universe is baby universe. We have seen that, and there was no galaxy, there was no stars that time. It's just hydrogen and helium, and that also from little late. Shuru mein, in the beginning there was nothing. Then space and time came, and then from space, some unknown energy created particle, and then that particles create the first atoms. And that is the time when this fossil radiation was. Isn't it fascinating that sitting here, we are proving 14 billion years back what has happened, and we are seeing it through our powerful telescope, and we are able to know about the universe. And that itself is a very, it's a deep, amazing achievement. So then you can see this red arrow. So as after fossil radiation, there was a dark age. We had to wait before the dawn happens. So the first dawn happens, and when the first star formed, and the JWST, there was a talk on JWST, I think here at AstroAdda, it is probing up to that first star formation. So after CMB, the first star formation is very long back. The Hubble cannot do that. And then after that, many other experiments have been happened. And then you can see billions of formation of stars, this tiny, and we are here today. But now let us come back today, as we are here today. So let us take our galaxy. This is our Milky Way galaxy, and there was, I used to have a T-shirt where there was a dot here, which is a little bit away from the center, to the one arm side, and it is said that you are there. They will draw sun there and say you are here, and there are 10 billion suns here, and who knows how many stars has Earth-like object or exoplanet. This research is also very active. So now, this is a beautiful structure, as you can see, very beautiful structure. In the middle, there is supermassive black hole that has also been discovered with the Event Horizon Telescope. And that black hole basically is holding the billions of stars. And I have told you in 1-2 sentences what is black hole. Yeah. So now, it has a beautiful structure. And remember what I said, what has structure, it has more than structure underlying. Something else. And what is that? The Vera Rubin, one of the first persons, she discovered that this galaxy, we all knew that it is rotating very fast. So you can imagine it's a tire of a car or the wheel of a car rotating tire. And now, if the tire has some water on it, suppose it goes through a mud or not mud, the rainy patch, it has water. If the tire moves fast, the water spreads faster because of the centrifugal force. So she was looking into the speed, because galaxy is rotating in a huge speed. The sun is in the galaxy and it is moving in 300 kilometers per second. Can you imagine? 300 kilometers per second. So she found that the speed which the outer edge, the stars or the visible matter is moving is really high, and there is not enough gravity inside to hold it back. Because we know how much gravity is there, because we know how many stars and what is the gravitational force of the stars inside. So she could not balance it. Later we came to know that actually whatever you are seeing is only tiny. There is hidden matter which is actually attracting and balancing that huge force of centrifugal force of class 11 and 12 for linear centrifugal force. That is called dark matter.
Your presentation has gone out of the screen. Can you just...
Again?
Yeah.
It has come?
Yes.
Yeah. So this inside is the hidden dark matter, which we don't see, and that is actually holding the galaxy together, and that is called dark matter. That is not the visible, and nobody can see it. But you need that to to balance the centrifugal force. So here is a beautiful picture of Diwali time from space of India. So wherever there is no light, it doesn't mean that there is not people there. Okay. And right side is the simulation of the universe. It's very looking similar. No? Universe is having Diwali pretty much every day. And we know if we take one point here, it's a very dense object where more structure has come, more galaxies there. Suppose take one galaxy, then you will see the disk is what I showed you before, but the blue halo is a three-dimensional, spherical halo, which is dark matter, which is actually holding the disk. So what you see visible is actually caused by the invisible. Now we know from mathematics and our simulation that without this halo, unseen dark matter, you cannot even produce the galaxy and cannot even hold it. It will be disturbed. So that is the beauty, that whatever is seen behind that, say there is something unseen underlying the laws of physics and the dark matter. And there has been many experiments, not only this one, the velocity I was talking about. I am not going to the detail who has all detected the footprint of dark matter. But we don't know what dark matter is. But do we really need dark matter? The answer is yes. From that fossil radiation, that tiny inhomogeneities from quantum mechanics, it is the dark matter which creates the whole visible universe, and then because of that only the galaxy can form. Without the presence of dark matter, the atoms cannot overcome the expansion of the universe. As I was telling you, space is expanding, it is taking things away, moving away. So you need some high force of gravity to hold it together, and that is dark matter. So let's see a short movie that how from tiny fluctuation dark matter creates the visible universe and the filament-like structure. It will come. All things comes because of the dark matter. So we are simulating the universe in a supercomputing facility. So you can see, if you take even a tiny dot here, it has so much structure. So this is the beginning. And then, as you wait, you will see that the filamentary structure will form. And it's almost look like the Diwali picture we showed you. And the black part here is empty space, void. The filaments are filled with galaxy clusters. So this is how the universe looks like. And if you look at a picture of our brain, it's a coincidence. The neurons also distribute like that. Very interesting. There is similarity in nature, the patterns and the structure. So now the most fascinating part of this video you will see that how from nothing, the tiny fluctuations from the baby universe, there was no galaxy, no stars, how the visible universe formed. And I will run a simulation in this video. You will see. So now let us take a slice of the primordial roughness which the baby universe gave us and see what is happening. It is the dark matter which is pulling things together and creating this filamentary structure. This is a simulation. You see the filamentary structure. And the universe exactly looks like that. So now we know that dark matter is inevitable, but what is dark matter? We know that they are there. Their gravity is doing that thing, but we don't know what they are made up of. We can only feel the gravity through this thing I showed you. But their fundamental nature, like we know the nature of electron, we know the nature of quark, we don't know what they are. And in fact, they are not made up of any of the known particle or particle physics which we have discovered over the last 50 years. So they belong to something else, and that's why we call them dark matter. So there must be a new particle of new nature, and we don't know what they are made up of. But we have to guess. If we have to detect them, we have to guess what they interact. But they don't interact like through like light. That's why they are dark. They don't interact through other forces. Only the weak nuclear force they are allowed to interact, other than gravity. And there was few scientists who proposed one candidate of dark matter, therefore weak dark matter, weakly interactive massive particle. People almost believe that we have discovered dark matter because the theory was amazing and it was solving many problems of particle physics. So we built so many detectors underground because we have to screen the cosmic rays only to detect the wind. So in Columbia University, where I used to study, they were the pioneer on that. Underneath the ground, 1 kilometer down, they have this xenon detector. And I did not work on that, but my friend worked on it. They will wait for whole 1 year. Every day they will go under and they wait for hit by the dark matter with their detector. And if they detect it, it will be a Nobel Prize, and they will detect their property. But for 9-10 years passed by, they did not detect. Now it is 20 years passed by. Many such experiments they did not detect the hit. So now it has been speculated that maybe we are going in the wrong direction. Dark matter maybe not weak. So there is another new avenue came up in dark matter research, which I also do. It's called can black hole be dark matter? So here the normal black holes, which Chandrasekhar proved that if its mass is less than 1.4 times solar mass, that black hole which we discovered from LIGO gravity wave, they cannot be dark. Okay, I'm not going to the detail. But the similar black holes or much tiny black holes can be formed during Big Bang. And they are around, they are here, they are in the, maybe in the room you are sitting, very tiny, like atomic size maybe or microscopic size, Armstrong size, they are moving around. And they can be dark matter. And if it is dark matter, then we are very in a nice position because you don't need to postulate any new particle, because black holes are made of normal particles, but they are different because they are black, means in the sense that they have the properties of dark matter because they don't emit light, so you cannot see them, but they have gravity. So this research is going on, that if we detect these primordial black holes from Big Bang, then the dark matter mystery will be solved. But till now nobody has detected, but there are a few experiments looking for it. And it will be this gravity wave, you can see, they will have their own gravity wave, and that can be detected or from the planet Earth. So now I will be moving to the next pillar, it's called dark energy. So it was the expansion rate of the space. So expansion rate of the space is something like that. You can see on the right side, in the Science magazine, they have written an article that's called Accelerating Universe. So they have put Einstein's picture again, because Einstein put the dark energy term in the wrong side, cosmological concept, because he wanted to stop the expansion. But we have to put it back in the other sign to accelerate the expansion. Because he was putting on the left side, we are putting on the right side of the equation. Just change of sign. Why? So to know that we have this beautiful discovery, and I'll just tell you, you can see me now. Suppose the space was expanding. You know, expansion of the space was like throwing a phone or throwing an apple. So if I throw this phone, it will move up, but it will slow down, and then it will turn back. If you throw an apple, it will happen like that. But imagine if you throw this phone and you are waiting and it crosses your rooftop and it is not turning back and it goes even up, it not even turning back, and up on its own force, it is moving and it is accelerating to the upward and process like a rocket without any fuel. That would be dark energy. So we were expecting that the space will move. Fast move is expanding, but it will slow down, just like an apple. That was the law from Einstein. But suddenly, in the recent past, in the history of the universe, somebody has pressed the accelerator and space is going very far. And that's why all the stars in that far away is moving away very fast. And this cannot be possible by any, because we know gravity is attractive. But here gravity is becoming repulsive. And it can only be possible through some unknown energy called dark energy. We don't know about dark energy, but we know it has a very peculiar property. I'm not going into the detail, and that's why, and it is everywhere. It is in your room, it is here, it is unseen, and it is 70% of the energy of the universe, and it is making the space expand. And I will show you one last video, and then we can have question. This video is coming. So before I go to the video, this dark energy has been discovered because of this, in the top figure left, you see a bright object which is equally bright like a galaxy. It is called supernova. Supernova explosion happens when a star dies, and Chandrasekhar talked about it, and when it explodes, it has huge brightness, almost like it is comparable to the galaxy brightness. And it like a fireworks in Diwali time. It runs, the firework runs for the brightness stays for 3 weeks and it dies down. But it becomes so bright that you can see them from far away galaxy. And thanks to that, because of that only you can see far away distance. And looking at the supernova and their receding speed, 2 groups of astronomers in US, Adam Beans and the other group in Berkeley, they discovered that actually the supernovas are moving much faster than expected. That means the space itself is moving much faster than expected, and that is the dark energy. Then they calculated the value of dark energy, and there was a mismatch, because in quantum mechanics or quantum field theory, they said that vacuum energy can be dark energy. And they said, wow, then we have a candidate of dark energy, vacuum, or the energy of nothing. I am not going to that. Nothing is not really nothing in particle physics. From nothing, particle comes and they march back. They are called fluctual. From nothing, particle and antiparticle can come and march back. So whatever you think nothing or empty space is not at all nothing in physics. And that creation of particle and their marching back create an energy, and it is called vacuum energy, and it has the anti-gravity effect. But unfortunately, the theoretically predicted value or the experimentally observed value by the Nobel laureate scientist is this 0.0000 less 1 times the predicted value. So there is a mismatch of 10 to the power 120 order. The biggest mismatch in the history of physics, where scientists predicted something and observed something, and the difference is 10 to the power 120 times higher. Means the dark energy is 10 to the power minus 120 times. This value is so tiny, and we have no idea from where these so many zeros have appeared, and this is called cosmological constant problem. But then you say, who cares? Erase 2 zeros. If you erase 2 zeros here, you will be also erased. Because if you erase 2 zeros, that means you are increasing the value of dark energy, that means you are increasing the expansion speed or acceleration speed, and you cannot form galaxy. It is a very fine-tuned balance between expansion rate and the attraction of dark matter. Dono milke together, they are balancing and forming galaxy. If you increase a little bit this side or that side, you will spoil the galaxy formation. If galaxy doesn't form, life is not there, and life is not there. Nobody is here to talk today. So we should thank the dark matter and dark energy for our existence. And what we see is just the 5% of the visible or 4%. Underneath there is a ice drop which is waiting to be revealed, and we don't know what is dark energy yet. Now I will show you a video, the fate of the universe, and we believe that if Big Bang has happened, there will be many Big Bang which will be happening from string theory, and each Big Bang will create one universe, and uniqueness of that so many universes, that each universe has a particular value of dark energy. So some universe has 0.01, some universe has 0.0001, some universe has and we happen to be in a universe that where we have 120 and 132. And that's why we are here, and that exactly balances the dark matter of the gravity and where galaxy or life can form. In other universe, if the cosmological constant is a little bit off, even 1, 0, 2, 0 off, with the same gravity, cannot create life. So we should owe our thanks to the value of cosmological constant. And if what will happen as the acceleration is taking over, after some time you will see acceleration is so high that even the nearby galaxy will be snatched away. If you wait for 3 or 4 billion years, it's not for you, future generation, if 3 billion years later come, and they will not see anything in the sky, because everything will be taken away by darkness and dark energy, and what will remain is the pure emptiness. Milky Way will be in the inside, there will be nothing but the beautiful universe you saw today. So let's see this video.
The Big Bang giving rise to our universe is likely not a one-time event. Instead, the fuel not only generates our Big Bang, but it would also generate countless other Big Bangs, each giving rise to its own separate universe, with our universe becoming but one bubble in a grand cosmic bubble bath of universes. And now, as we meld this with string theory, here's the picture we're led to. Each of these universes has extra dimensions. The extra dimensions take on a wide variety of different shapes. The different shapes yield different physical features. And we find ourselves in one universe instead of another simply because it's only in our universe that the physical features, like the amount of dark energy, are right for our form of life to take hold. And this is the compelling but highly controversial picture of the wider cosmos that cutting-edge observation and theory has now led us to seriously consider. In the very far future, those galaxies will rush away so far and so fast that we won't be able to see them, not because of technological limitations, but because of the laws of physics. The light those galaxies emit, even traveling at the fastest speed, the speed of light, will not be able to overcome the ever-widening gulf between us. So astronomers in the far future, looking out into deep space, will see nothing but an endless stretch of static, inky, black stillness.
So this is my last slide. So we live in a time where, in cosmological time, where the highest amount of structures and the beauty, the firecrackers of all the galaxies are visible. If you have been before the life would have come, then you will not see so much variety because they have not found that. But if you come later in cosmic time, few billion years later, universe is 14 billion years old now. Who knows? Maybe how many few more billion years. But if you wait for another 3-4 billion years, in future astronomers come, they will not see anything. So we are living in a very beautiful time where universe is revealing itself, its beauty to us, and it's fascinating. So we should really thank the invisible to make us visible. And thank you so much.
Yeah. Now, so we start the question session.
Yeah.
And I think some questions are already there in the chat box, which I will read one by one, and maybe you can give some light on those. One of the questions says that what is the difference between a blazar and a quasar?
So that is not the topic of.
Yeah.
You can just search in Google. I will not go into that.
Yes.
But quasars are much more, the very bright object, and maybe we will skip that. It is
Yes.
not related to today's topic.
Yeah. And Mahesh Shetty, he has given one or two one question and some comments. Fermat's principle can explain in a better way using Huygens principle, with every point on wavefront act as a secondary source which gives constructive superposition during certain path. Can one give similar explanation for curved space-time?
No, it is not possible through that. It is not. You need Einstein's equation, which you don't need. Fermat's principle doesn't need Einstein's equation. And space-time cannot be described by Fermat's principle. You need Einstein's general relativity. Yeah.
Yeah. Next question is time travel possible, and if so, how can hypothetically it be achieved?
So there has been many movies, interstellar movies. So till now, the wormhole you can know the wormhole if it is there, but we don't think there is no scientific basis here. So I don't know. I mean, if it is any technology comes, till now it is not possible yet in the technology. Okay, so it's up to future.
Yeah. Next question is based on a simulation which you showed that out of nothing the structure has evolved.
Yeah.
And it is said that the simulation is similar to how stars form due to collapse of large nebula. So these two simulations appear similar. That is the statement which is made, and it is asked that is this obvious? Is it obvious? That
No, I did not make that statement because this simulation is done. Not the stars from that nebula. It's different.
The question is that whether here the person who is asking the question, he says that he has seen somewhere else a simulation of a star, and this is appearing somewhat similar.
Okay.
So whether it is obvious means whether it is
No, not at all. Because here it is the dark matter cosmic wave forming from billions of years, whereas nebula form stars is completely the gas collects and the star form. It's very different. There it comes in one central point of star, but here it creates filament. In star formation, you don't create filament. From nebula to hot star.
Yes. The next question is that has the universe been accelerating from the beginning, or did it start accelerating at some later point of time?
From later point, that's the beauty. Because if it was accelerating from the beginning, gravity cannot win and create galaxy. That's why its value has to be exactly that many zeros so that it starts a little bit late. It started after 8 billion years. So after first 8 billion years, it was not accelerating. That's why the formation of galaxy was almost done. The seed formation. Yeah, nice question.
The next question is, can black hole penetrate the space-time fabric?
That is a speculation because it's not that black hole penetrate. If you fall inside the black hole, there has been speculation that because space-time structure breaks down. So, but the question is, if you penetrate, where do you go? You go to another space-time, that is unknown because when the space-time structure breaks down, your mathematics also break down, your predictive power also break down. So we don't take it into the part of physics because it's unknown. cannot say talk about. It can be philosophy.
Next question is dark matter made of axions?
So there is another possibility that it can be axion, but it can be black holes, primordial black hole, or it can be other particle, but nobody knows yet. But axion is not ruled out. There has been some experiment planned, so if we are lucky, we might get it.
The next question is, what have we found about antimatter?
No, it is there. Like matter is there, antimatter is there. It is being produced even in CERN, Switzerland. It's not so much mysterious anymore. Positron, even the positron has been detected from the stars. Electron and positron get separated, and positron comes, and there is this Pamela satellite has detected positron. So we deal with matter and antimatter in accelerator or from the space also. Yeah.
The next question is, are primordial black holes exist? Means what is meant is, does primordial black hole exist, or they are just some type of hypothesis?
So theoretically, it's not just an hypothesis we do. It has to be consistent with equations, Einstein's theory. They are all consistent, and they are consistent with Big Bang. So when we hypothesize in modern cosmology something, it's very hard to keep it alive because some experiment or some model or some theory rule it out. But till now, primordial black hole looks okay. And the thing is, if you find a black hole which mass is less than 1.4 times the mass of Sun, then it is primordial, because the stellar black hole can only form from Chandrasekhar limit when the mass is more than 1.4 times the mass of Sun. So if you find a subsolar mass or less than solar mass black hole, then you know that primordial black hole exists. And who knows, we might find that. There is a huge research. I have even done it in the conference here in Bangalore, only on primordial black hole. Yeah.
The next question is, can the dark matter of another particle, which can be explained by modified version of standard model, can the dark matter be another particle?
Yeah, it can be, but then it will not be part of standard model. And we do not call it as modified standard model. Standard model is standard. We call it beyond standard. So if you find something other than this particle, the standard model, we call it beyond standard model, not modified. Yeah. And that will also get a Nobel Prize, definitely. Because every fundamental particle, when it is discovered, it is Nobel Prize. Because it is like a building block of nature. Yeah.
The next question is, the person who is asking, he says that you mentioned about dark matter is responsible for final shape of black hole. The changes in universe, final shape of black hole and the changes in universe. So can we consider it as a hypothetical particle graviton?
No, dark matter is not responsible for final shape of black hole. No, black hole is formed from star collapsing. It has nothing to do with dark matter. So, I think you misheard. So, black hole and dark matter are separate.
Then we have one more question. Why does the rotation curve of galaxy increase with increasing distance near the galaxy's center? Means rotational curve. They are asking the shape of the rotation.
So that is a very easy mathematics using centrifugal force. You can derive it. It goes increases like a straight line, flows to the galactic center, and then it becomes flattened out. So I will not do the mathematics here. You can search. It's very easy. You just take the class 12 mathematics. Okay, you can do it with some approximation. So it's just centrifugal force you balance with the amount of matter you have. 4/3 pi r cube rho, then you get it.
Next question is, if the universe is expanding, is it expanding to another universe or to space in between the universe?
None of them are right. Okay, it is expanding into itself. So now think about it, it is not so easy. Okay, even I took 8-9 years to understand it. It is like a wavelength is getting stretched. So all you are seeing, suppose you start with a 1 micrometer wavelength, and as space expands, it will become, say, after some million years, it will become 1.5 micrometer. That's what we see, that everything is stretching. But we don't go to the boundary of the universe, so we don't know. Maybe it is coming back into itself. It's a very different geometry. Your mind cannot understand. That's why GR cannot be understood by the five senses, even in mathematics. So like that, it is expanding into itself because there is nowhere else to go. Okay? So, think about it. It's not easy.
Yeah. Next question is, will the universe always expand or recollapse?
No, in the present understanding, if dark energy, the way we understand, it will continue expanding and accelerate, and everything will go away from each other and you will get in the nothingness. But somehow, if things change, like dark energy has started dominating just after 8 billion years, who knows? Maybe something happened and dark energy switch off again. Then it may collapse, or something may happen some other. So there are models where it is said contracting universe. You expand and you contract, and again you expand and you contract, and you continue like that for eternal. They are called equinotic universe, but it has a lot of problems. This theory is not accepted so much. Yeah.
Then next one is, after Big Bang, how many time, means how much time or at what duration of time, that's what is meant, electron, proton and neutron are formed?
Yeah, they are called Big Bang nucleosynthesis, BBN. So you can just go to any book. So it's like first 3 minutes is the time when they are formed. First 3 minutes after it.
At Winberg's books.
Yes.
Stephen. Okay. So next one is that, what is the role of dark energy in precise value of cosmological constant? How exactly it is calculated?
So the dark energy value is observed, it is not calculated. But cosmological constant is one candidate of dark energy whose value has problem of 10 to the power 120 times higher. And nobody knows about the solution. So till now cosmological constant is not dark energy because we don't know it's why how to manage this 10 to the power 120 zero mismatch. So that's the answer. That's why it is called one of the biggest problems till now. Everybody is scratching their head, including string theorists and nobody knows.
Next one is that, which method is more accurate to find the expansion rate of the universe in between distance ladder method? LGM method, parallax method, Schu's method or something else?
And this is much more technical question. So the parallax method and there are few other methods, that gravitational time delay method, all are being used, and I don't know which one is accurate because people who do one method, they say think the other ones are not so good. So they are competing with each other. But Schu's team has not found any systematic tips yet. So they are claiming that they are very high quality. The atom is the same guy who got Nobel Prize. So if he finds this measurement of Hubble constant, he might get another Nobel Prize. Yeah. So who knows?
Yeah, that ends the question in the chat list. If anybody else wants to unmute and asks one or two questions, we can allow that.
But I think we have got a lot of questions. But
yeah. People are very enthusiastic, so that is good.
Okay, great.
I think nobody else is there. So we will do one thing. We will conclude this today's session. I thank Professor Shubinoy Das, who have given a wonderful talk with lot of animations and video, and our viewers are also very eager to ask lot of questions, and they were very enthusiastic in going on asking questions. So last question, just now somebody put that is black hole dark energy? I think this is the last question.
No, it's not. I have told. Black hole is collapse of the normal matter, whereas dark energy we don't know what it is. And I have given my Gmail ID in case people are enthusiastic, these have a lot of interest. So Gmail.com, they can ask me that.
Yes.
Or they can ask you.
Yeah. And so this
Sir,
is.
I have one question.
Yeah,
I want to ask a question.
Please ask.
Sir, is there any difference between spherical stars or variable stars?
Oh, that is also not part of this talk, but I can refer to you. You can write to me or I'll discuss to you later because it is not at all related to today's talk. Okay, I'm just taking question because astrophysics is a huge subject. so that ice breaking. But you can write to me later, or you can find the variable stuff. And there are huge amount of research work happening. Okay, or I can give you some reference there.
Yeah. So we thank all the viewers, and this is the joint program between Regional Science Center and Planetarium Calicut and Public Outreach and Education Committee of Astronomical Society of India, and we bring in every month a new topic with a new speaker who speaks and delivers on the topic. I again thank Professor Dr. Subinoy Das to have spent time with us and answered so patiently all the questions one after one which people have asked him, and thank you so much. Thank you very
Thank you
much.
so much.
Yeah.
Thank you.